to me, the main lesson about the core of climate science is kind of how stable it's been and how little things have really changed. I think we've learned a lot about risk to humans. So, for example, there's been a huge amount of knowledge from economists in the last 10 years that's really helped to teach us that high temperatures really kill people and reduce productivity. We've learned a huge amount about how to cut emissions, like the big improvements in solar power. But the core of climate science has been really pretty stable. My view is that anybody who says that they know solar geoengineering is a good idea or that they know exactly how to do it is just talking nonsense, but that there is enough reason to believe that it could really reduce human and environmental risks during this century that it's worth us, at a minimum, taking it seriously.
Welcome to Straight Talk, a podcast about big ideas featuring candid discussions with some of the world's foremost thinkers and doers. I'm Hank Paulson, chairman of the Paulson Institute, and today I'm speaking with David Keith. David is a professor of applied physics and public policy at the Harvard University School of Engineering and Applied Sciences and the John F. Kennedy School of Government. He has worked at the intersection of climate science, energy technology, and public policy for 3 decades. He is best known for his work on the science, technology, and public policy of solar geoengineering and led the development of Harvard's Solar Geoengineering Research Program. He was one of Time Magazine's Heroes of the Environment. David is the founder of Carbon Engineering, a Canadian company developing technology to capture CO2 from ambient air. David, welcome to the podcast. You're a real pioneer on the cutting edge of science and policy, and someone who's been way ahead of so many others in understanding the implications of climate change. I'm really looking forward to today's discussion. So let's start at the beginning. You grew up in Ottawa, Canada, and your father and stepmother were both environmental professionals. Talk a bit about what you learned from them at an early age. And who were some of your other mentors?
Well, yeah, thank you. It's a thrill to be on this thing. So certainly growing up in a family of people who worked on environment and in government and dealt with the hard deal of making environmental compromises with science and government was a lesson. But I would say personally, you always have to kind of think you're breaking from your parents. So I got really hooked up with a guy called Paulson, who was a physicist and in hindsight, one of the really top physicists on the planet. And I was lucky enough to start working in his lab in high school and getting to play in this lab filled with lasers that were literally the size of a house. And that was an extraordinarily kind of happy moment. And it really got me eventually into MIT for grad school and so on. But also, especially in those days, it got me eventually in contact with a bunch of people in the physics world who thought hard about public policy. So I'd say, I grew up worrying about the environment, but also worrying a lot about nuclear weapons. And coming to MIT, I was lucky enough to get to talk to folks like Henry Kendall, who founded Union Concerned Scientists, and Phil Morrison, who worked on the original Los Alamos project and was sort of deeply thoughtful about policy. And I think that era and that community, the physics community, really thought hard about the implications of science for public policy that really mattered.
Now, I can't believe there are a lot of 16-year-olds that were looking to get hooked up with a world-class physicist, right? When I was 16, I was wondering about how I could go fishing up in Canada or whatever. So you must have had something special either with your parents or some teacher that really saw this extraordinary interest and figured out how to make that connection, right?
I guess so. I was an odd kid. I was dyslexic, so I was actually pretty slow to learn to read and write. And I think I had those skills, but I think part of why it worked so well with Paul is gave me a chance to do a bunch of hands-on stuff where I wasn't obviously a superstar in high school at all. In fact, I failed classes, but I think Paul gave me a chance to really find stuff I was good at, working with my hands in the physics lab, and that kind of unlocked my ability to do the next thing.
That makes such a difference, these early experiences. So describe your approach to climate science.
So I think it's been kind of what I might call a blue collar approach. When I stepped away from the physics world, I went through physics grad school, but then got interested in climate. I've always been interested in the applied side. So there is some beautiful high science in climate for sure, and atmospheric science, but I've always been pragmatic and I've often worked on hardware. So the first real big thing I did was working with a group at Harvard to try and develop a satellite that would measure temperature of the Earth accurately from space. And surprisingly, we still do a kind of crappy job of that. So that was really kind of practical instrument development. And then I got more involved in the energy policy side and working with people in the energy industry, trying to understand how we could cut emissions. So I definitely do climate science in the sense that I've run climate models and fooled with the Fortran and big supercomputers, but always with a kind of pragmatic applied focus, not trying to push the scientific envelope, but trying to do things that help to do useful public policy.
Yeah, and you can just see that in your work. So let's now talk about, climate science and how it's evolved. So tell us a bit, over the course of your career, how has it evolved? And of course, what do we know now we didn't know 20 years ago or even 5 years ago? And so let's start there.
So, in some ways, for climate science, I think the answer is we've learned surprisingly little that's new that really matters to public policy. So, it's still true that we know that warming is roughly proportional to cumulative CO2 emissions. We've known that for decades. It's still true that there's deep uncertainty about, in a sense, that proportionality constant between how much we emit and how much it warms. That's called the climate sensitivity. And that was first really estimated by something called the Charney Commission in 1979. And, we know an enormous amount of details compared to 1979, but that big uncertainty, the fact that we're going to roll the dice, we are rolling the dice every day, and that we don't know for sure how much it will warm for a given amount of carbon dioxide, that the uncertainty is roughly a factor of 2 or 3, that's been kind of constant my whole career. And I think we sometimes get sucked into the assumption there's a lot new. And that comes from a kind of a hype cycle in the media where people publish new papers that are legitimately great papers. Each piece of science does its thing. But then the news media has to report what's news. And so each of these things gets reported as if it's some really new thing. Whereas in practice, to me, the main lesson about the core of climate science is kind of how stable it's been and how little things have really changed. I think we've learned a lot about risk to humans. So, for example, there's been a huge amount of knowledge from economists in the last 10 years that's really helped to teach us that high temperatures really kill people and reduce productivity. We've learned a huge amount about how to cut emissions, like the big improvements in solar power. But the core of climate science has been really pretty stable.
So, given that it's been stable and based on everything you know, how would you define the climate challenge we are facing today? And how concerned should we be about the climate threat?
I want to try and argue this sort of from both sides. On the one hand,
Okay.
when I think about really acute risks to humanity, to even the world's poorest, or to my children, I think climate change doesn't quite meet what I see as kind of the existential threat risk. So I think a really terrible risk that might happen over the next, say, half century, my top candidates would still be nuclear war or a pandemic, perhaps a pandemic with deliberately modified organisms. The pandemic we've had has been, look at the enormous way it has reshaped our society. And yet it was a very low mortality rate infection. You could imagine much worse pandemics, and we've gained lots of them out. So in that sense, I don't think climate change is quite like that. On the other hand, climate change is a terrible problem because it's by far the biggest global scale environmental problem. And it has this sort of awful cumulative nature that makes it really hard to solve in the sense that the climate risk is proportional to cumulative emissions of CO2. And that means that on any given kind of political cycle, 5 years or something like that, there's not that much benefit in cutting emissions because of that cumulative nature. So we must cut emissions, but it's really hard to do, hard to coordinate globally. And that means we keep having more and more CO2 in the atmosphere and the risk keeps getting larger.
So that brings us really to my next question. So you're someone who is, I think, very special because you know the science in and out, but you've also been very tuned into public policy for a good while. So, what do you think are the most important domestic policy response the United States should take to mitigate the climate challenge? You've talked about why it's so difficult, and it's enormously difficult politically because it's long term, as you said, and because it's global. But what should our domestic response be?
I think the central thing is decarbonizing the electric grid. That's not the whole story, but for so many things, decarbonize electricity first and then electrify what you can. And I think we've, in a sense, done some of the easy part. So the extraordinary rollout of solar and wind really has been a triumph and a triumph of innovation and science. But now it gets harder because if you really want to squeeze most or all eventually the emissions out of the electricity sector, you've got to deal with the seasonal cycle and the daily cycle of those energy sources. And you've got to deal with long distance transmission. So if you really want to do it with solar and wind, you've got to build out a national grid in a way we never have before. I mean, alternatively, you could do it with nuclear power, but those are basically the main pathways to do it at scale. And all of those require something more than just policy that incents emissions cuts. So we certainly need policy that puts a price on using the atmosphere as a waste dump. So that might be, carbon taxes or some other kind of carbon price. But that alone, I believe, will not do it because a bunch of these things involve really hard infrastructure choices that involve trade-offs. So to make that less abstract, if you really want to build the kind of long distance transmission network we need and get those lines sited in a reasonable amount of time, you have to have a level of federal power to say that this line is going to run through here. And if local farmers don't like it, they need to get compensated. They need to have a fair hearing. But in the end, we have to be able to make decisions and put those lines in. And that means in some cases, not to be apocalyptic about it, but you're going to have standoffs. Well, local farmers are going to be there, maybe even with their guns, saying they don't want these things done. And we have to have a social way that we can resolve that problem.
There's also in our federal system, there are constitutional issues in
Yep.
terms of what the federal government can force. I remember how frustrating it was for me as I started, doing work in China and recognizing that they could build, a long distance grid that, was DC and then converted to AC and do it very quickly. And we had the technology. We're ahead of them in the technology, but we can't implement it. It's just so politically difficult in our system.
Yeah, I think it's really, I mean, I don't want to throw away the easy stuff. So some of the easy stuff I think will happen and almost certainly will happen in this Biden administration is much more spending on R&D, which is certainly worth doing, and something that effectively puts a higher carbon price on and drives, more electric vehicles and more grid decarbonization. But if we're really serious about actually driving the whole economy towards carbon neutrality on a scale of a few decades, then you've got to do a lot more than that. And some of those things really do involve something that's a lot closer to hard industrial policy. How we're really going to deal with steel and concrete and heavy chemicals, how we're going to deal with the grid. And I think those things require a level of intervention in the economy that's really challenging because I do think it needs a level of federal power and intervention. And yet, uh, I don't believe that I want the federal government micromanaging everything. And figuring out how we make that balance, I think is going to be really tough as we get serious.
Yeah, how you rewire an economy. And as you said, getting beyond even electrification, how we think differently about making steel, making cement, making plastics. It's a huge challenge. I want to move from the domestic to the global. So, it's a terrific thing that Biden has rejoined Paris, right? And climate diplomacy will be important. But, as we've talked about, the world's leading economies are nowhere near close to being on track to meeting the goals set out in the Paris Agreement, which should keep global temperature increases below 2 degrees Celsius by the end of the century. But even if we meet the Paris targets, our world will still undergo significant weather-related shocks. And the voluntary targets, as important as they are, they're just not sufficient. And so, do you have any suggestions for improving the global governance process?
That is the very hardest problem. I think it's important to say the essence of Paris. When people talk about Paris, they think about that 2-degree aspirational target. But the essence of Paris is really nothing more or less than a pledge that governments will make plans for cutting emissions and then periodically review those plans.
Yep.
And so to me, Paris doesn't actually prove anything in terms of emissions, but it's a very important framework for countries to negotiate how to really drive emissions down. But that hard work is really about, fundamentally, it's about coupling national level economic pain, because fast emission cuts are going to hurt. They're going to cause economic pain. And having a way that countries can not hurt themselves in terms of their competitiveness with other nations in trade. So to me, the key aspect is basically that Paris provides a forum, but it doesn't provide the answer, where countries can take national actions to cut emissions and have some level of negotiation about fairness, so their trading partners are taking similar actions, so neither side is disadvantaged and everybody gets the public good advantage of less emissions. But it's hard, and I think we're going to have to tie this into the global trade system, to the WTO, more tightly than we do now. I think we will have to have something that looks like a carbon border adjustment to try and lock in national policies and make it harder for any nation to backslide to focus on their near-term benefit.
Yeah, you and I are in strong agreement on that. And, I've said Paris is good, it's necessary, as you say, it provides a framework, but it is not helpful to the extent that people think sort of joining it or that these voluntary targets, are the answer. And, I've sort of thought we should do something along the lines of what President Bush put in place when I was Treasury Secretary, which was the major economies, getting this major economy forum together. Because if you get the major economies, you deal with most of the issue, so that still exists. But then you need to come up with a way to deal very directly with this incentive you talked about, or to free ride, right?
Yeah.
And so to sort of look for a short-term advantage for your economy and free ride. So you need to do away with that. We need some mechanism that's got real teeth in it and real incentives to curb emissions. And so there's going to have to be something. And I think your idea with the WTO mechanism with a border adjustment is one interesting way of dealing with that. So David, now let's talk about technology. You've been at the cutting edge of developing a technology called direct air carbon capture, which is designed to remove some of the carbon dioxide already in the atmosphere. And you're the founder of a carbon capture tech company. Given our current trajectory, are we ultimately going to need to do something like this to save our planet? Yeah, how practical is it? As I look at it, and I look at how difficult it's going to be to slow carbon emissions, you'd like to have something where you could recapture carbon. So talk about this technology.
So there's no question that some forms of carbon capture are technically possible. The issue really is all about how much they cost and what their local environmental impacts are. And assuming we can get carbon capture from the atmosphere at a reasonable cost, then to me, it's part of the big picture of what we do. Or to step back, the things we basically do are cut emissions, capture carbon from the atmosphere after emitted, do this solar geoengineering stuff we'll talk about later, or do local adaptation measures. Those are basically the four big things we can do about climate. And in thinking about climate policy, I think we have to think in those four dimensions. So the story of carbon engineering, this company, I found that is kind of fun because it's an illustration that until people really begin to work seriously on something, you don't know what it costs. So there were previous estimates that it would cost $1,000 a ton or more to capture CO2 from the atmosphere. And those estimates were by really smart people, but they hadn't rolled up their sleeves to actually do the practical engineering to see what it cost. And that company started not with me thinking I wanted to found a company at all, but me thinking that I wanted to challenge some of these assumptions by going out to industry and saying, what would it cost, just as an academic exercise, to do CO2 capture from the atmosphere if we assumed we use the maximum amount of existing technology? So we said we're going to use things like forced draft air cooling towers that are absolutely standard commercial equipment, and a back end that's a lot like what's in pulp and paper. And we said, if we're going to string this together with existing costs, what would it be? And that was really originally just a policy analysis exercise. But then as we got going and I invited some people in to critique us, they said, well, why not start a company and actually begin to drive this more forward in a serious engineering way? And I ran the company the first 5 or so years of its existence. Right now, I'm not that involved. It's doing very well. But it was extraordinarily fun to really, in a company environment, as opposed to an academic environment, just do that kind of very much blue collar engineering, working with individual equipment suppliers and with larger engineering firms to see how you could do practical carbon capture from the atmosphere where you do it at the minimum technical risk and at low cost. And that's really where we drove the whole 10 years now of carbon engineering.
Well, to me, it's fascinating because, as you've said, you sort of need an all of the above approach, right? This is cumulative. So we need to be doing everything we can to slow the rate of emissions and decarbonize our economies. But, at the end of the day, if that's not enough, and it looks like it very well may not be enough, we're going to need some breakthroughs. And so, when I first heard some of these cost estimates, I said, oh, we can never spend that much. When I look at the fact that the US has already spent, about $5 trillion, in responding to the pandemic, and you look at the stakes here, some of those numbers don't look as unreasonable to me. But I got a last question before going through direct air capture. If we're willing to spend the money and you drive the cost down, can this be done on a big enough scale to make a difference? How do you think about that?
Yes, and I definitely am not thinking just about the technology of my company, but I think there are a
Right.
range of different options for carbon removal, including biomass with capture, where I actually was also involved. I had the first PhD on that topic, and really a big range of different direct air capture technologies from competitors to carbon engineering. And then there's separate ideas for adding alkalinity to the ocean. So I think there's no question that some of those could work. But my biggest lesson from carbon engineering is really how extraordinarily hard it is to know how much things cost, and how the climate world is filled with academic estimates, some of them from very, high powered people who think they know what stuff costs. And I found it really quite a lesson that's made me, frankly, less proud to be an academic, because it turns out to be very easy to get, professors from Harvard or wherever to opine about what some future technology will cost. But the honest truth is you just don't know until you really do the engineering and the hard work. And if it was really possible to have people just know in advance what technology would cost, then the venture capital industry would hire those experts and they'd get it right all the time, but they don't. So if you think people always want to know what it costs, there was original estimates of 1,000, and then people throw around numbers like 100. But even if you ask me, stuff I can't quite tell you from private information inside carbon engineering, carbon engineering has now spent, of order $100 million of development costs. I mean, really big money. It's a lot of work as a 100-employee company, but we still don't know what it costs there's still significant uncertainties, because the real world is, until you actually assemble this hardware and run it, and until you build the second generation, you just don't know. These things are uncertain.
I'm so glad you made that point because I've seen it in so many of the areas where I'm involved. I love the natural world. Maybe in a different life, I would like to have been a naturalist. I'm out in wild, beautiful places all the time. And it's fascinating. I'm interested in things like falcons and birds of prey. And it's amazing when you talk to the people that have done the academic research and what they don't know as compared to those that are out in the field all the time. And some that have no degrees at
Yep.
all, but
Yep.
what they know and what they've learned through their observations. So it's really key.
I mean, let me just pile on, because I think it's interesting to say that I think there's a real challenge that for climate science, you want scientists, no question. You want elite academic scientists. But for energy technologies, there's a problem that a lot of the political discourse and the press get shaped by papers that come out of, Stanford, Harvard, MIT, whatever. And in some cases, those are really from academics who are pretty removed from the practical industrial realities of actually getting technology out there and permitted. So you tend to get these papers that have, two significant digits about costs. And as I've got being an academic, but now being more involved in actually seeing real industrial costs inside one company and being involved in a bunch of other peripheral things, I'm conscious of how deeply uncertain these things are, and how these statements, both about the way, say solar power costs will go, where I got to admit, I was dead wrong. I thought solar power would never decrease in cost as quickly as it did. To other cases, like, why on earth nuclear power has been so expensive. When you really get under the hood and talk to people who are involved in the contractual details and the engineering details, it is very hard to figure out what stuff costs in advance.
And nuclear power is depressing to me because the United States has stepped out of the game. If
Yep.
you want to work on a nuclear plant today, you have to go and work in China. And our government has made it very difficult for people in our very best labs to go do that right now.
Yeah.
If you want to make breakthroughs on fusion, you're not going to do that just in a lab. You're going to have to, and people like Bill Gates who've done real work in this area, have essentially been shut down, right? Because you can't build nuclear plants outside of the US in many places around the world, and because you'll run up against our national security laws. So I want to move to another controversial area. I remember I first heard about this. I had a family member who was talking to me about, this conspiracy theory,
Hmm.
jet trails, and looking up at that, and I was convinced that our government was doing geoengineering. Now, you've written a lot about what is a very controversial area of science, solar geoengineering. So I'm going to want you first to talk a little bit about, just a simple primer on climate science. Why is the Earth heating up? And then why is geoengineering one of the potential remedies? And then I'm going to want you to talk a little bit about your work here, why you think it's important, and how you think about the benefits of geoengineering and how you weigh them against the risks.
That's a big list. Well, let's start with the basics. Why does carbon dioxide warm up the Earth? Carbon dioxide warms up the Earth because it absorbs infrared heat, the kind of heat radiation you feel from a warm heater. And in absorbing that heat, it makes it harder for the Earth to radiate away energy. Now, the Earth is always in kind of energy equilibrium. So the energy that we get in from the sun, we have to radiate it back as infrared. And if the added CO2 makes it harder to radiate away the infrared, then the Earth has to be warmer in order to come back into balance. That's why CO2 warms the Earth.
That's what people call the greenhouse effect, right?
That's exactly right. And so the idea of solar geoengineering is that humans might deliberately make the Earth a little bit more reflective, so there's a little bit less sunlight absorbed, and that would help to get closer to the original, before humans messed with it, equilibrium. And that also gets at one of the key reasons that it's never going to work perfectly. So while solar geoengineering might, and we can talk more about that, really reduce climate risks a lot, turning down the sun is not anti-CO2. And there's no way that reducing the amount of sunlight will perfectly compensate for the warming effects of added CO2.
Okay, so now talk about what you've learned, what your research has shown, and why you think it's important to continue that research, and what are some of the political issues involved here.
So what I think a range of research has shown, and definitely not just mine, is that from really basic theory and from every major climate model, we've learned that solar geoengineering, if you did it in a way that was pretty even around the world, that it really looks like it would reduce many of the key climate risks that concern us, not just temperature, but it would reduce extreme storms, sea level, et cetera. And there's evidence from these models, it might be wrong, that it really does it in a pretty even way, that really most places on the planet would see most climate variables reduced if you did this. I think the central challenges are the following. First of all, there's a deep political challenge, which is about the idea that this might encourage us to do less to cut emissions. So this is, to be clear, a kind of Band-Aid. It's an inherently temporary and imperfect solution with a bunch of risks. And at best, what it does is it limits the risks of CO2 in the atmosphere. And if we use that as an excuse to put more CO2 in the atmosphere or slow down emissions cuts, then we could end up getting in an even more dangerous situation. That's often called the moral hazard of solar geoengineering. And I think much of the opposition to even research on this topic comes from fear that even if it in principle could really reduce risks and save lives in the next half century or century, that it will be misused as an excuse to keep the fossil fuel party going. That's really the core of the political challenge. And then coupled to that political challenge, there's the technical challenge that because of these fears about research, we're not doing much research. So while there are reasons to believe it could be actually very effective at reducing climate risks, we just haven't had a serious scientific and technological effort to really know more.
Well, so explain, but geoengineering, so how would you affect it? What would you release in the atmosphere?
Well, there's actually a whole range of ideas for how to do this. So going right from the top down, in principle, you could put structures in outer space in between the Earth and the sun that would reflect away from sunlight. I think that's ludicrously expensive and not realistic for the next half century, but in the later half of this century, it might be plausible. We've had some serious meetings about that now. The one that I think almost everybody agrees is most easy to do and that is global scale is adding aerosols, fine particles like dust or sulfuric acid to the stratosphere about sort of 20 kilometers over our heads. That's about twice as high as a regular commercial jet aircraft flies. And those particles stay in the atmosphere for about 1 to 2 years. So you have to keep putting them in. But on the other hand, that means you could try putting some in, work your way up a little bit, and then if things didn't work out, work your way down a little bit. But there's also ideas for altering some thin cirrus clouds that could let infrared radiation out better, which in principle might be a better way to cool the poles. And there's ideas for making certain kinds of marine boundary layer clouds, the kind of stratus clouds you see off the coast of the UK or Seattle. There are ways to make those whiter, and there are more ideas still. So there's a big range of ideas about how to do this, but they all share the property that they are about deliberately altering the radiative balance of the Earth. And they all share the property that at best they'd be masking the underlying danger from increased CO2.
And also, it would disproportionately benefit some areas and regions that hurt others, right? Because even though it may have the same impact, some parts of the world are going to have some benefits, at least in the short term, for climate change, and others are going to be disproportionately hurt.
Yes. So it does appear from the climate models that you could do this in a way that was very even globally. But it turns out that the benefits go most to the places that are basically most harmed by high temperatures. And that's really the world's poorest. One of the only papers I know that's looked seriously at the impact on global inequality using this modern econometric data on how temperatures impact productivity, we find that if you did solar geoengineering, it reduces intra-country inequality substantially over the next sort of half century, which is, I mean, a huge prize potentially in terms of human welfare. But that again gets to why this is so politically fraught. My view is that anybody who says that they know solar geoengineering is a good idea or that they know exactly how to do it is just talking nonsense, but that there is enough reason to believe that it could really reduce human and environmental risks during this century, that it's worth us at a minimum taking it seriously, which to me means having a really deep research program, developing these technologies, and really beginning the serious conversations about how we would govern it.
So, David, we've now talked about two technologies that I would consider breakthrough technologies, right? We've talked about direct air carbon capture. We've talked about solar geoengineering. So, help our listeners understand other types of technologies that are making the biggest difference today, or other technologies that are potential breakthrough technologies.
So I think by far the most exciting thing in technology in the last decade or two for me has been the extraordinary drop in the cost of solar photovoltaics. And it's really this interesting case where there were all sorts of ideas for new solar technologies, but what's happened is silicon solar cells have just kept getting cheaper. And the combination of that and the fact that electrolysis for taking electricity and making hydrogen also has got a lot cheaper, I think is opening up a really new possibility in the energy business, which is that you could build, multi-gigawatt solar photovoltaic installations in really sunny places, couple them with electrolysis, and make solar hydrogen at prices that are really interesting, prices that are, of order $10 or $15 a gigajoule. So that's, not that much higher than the price that Europeans or Japanese pay for natural gas. And there's no limit to that. There's not a land use limit. There's not all these technological scaling limit. That doesn't magically decarbonize the world because hydrogen is a lousy fuel. It's hard to move it around. But I think it really opens a new pathway for how we could really do decarbonization that I find really exciting. So to me, solar power has been the really exciting, scalable thing.
Yeah, it's been huge. And there's some places in the world right now where it's really close to grid parity, economic parity, and that is huge. So let me switch a bit now. When you're not wearing your scientific academic hat, how do you spend your time? What other interests and hobbies do you have, if you have some spare time? Yeah.
Well, I've been taking a little more actually during pandemic, being 57. I love being outside. So we do all sorts of things where I'd say the biggest is climbing. So we climb a lot, kind of obsessively. I think I was counting the number of routes that I did as a lead climbing routes this year, and I was over 200. And, I'm actually just negotiating with a friend about where we're going ice climbing tomorrow. So
To tell me about some of the routes. I used to have my heart in my throat because I have a daughter that would do ice climbing and go up, the most difficult winter routes up Mount Rainier and those kinds of things. So tell me about where you've climbed.
Well, so I'm long-term home is in the Canadian Rockies in Canmore, Alberta, which is where I am right now. And what's great about this is they're a mountain town, so I can look out my window literally right now and see some of the faces that we've climbed. So the most recently, my wife and I went up to do something called Weeping Wall, which is up near the middle of the ice fields in between Banff and Jasper. And that was
Wow.
fun because I remember I first saw it probably 25 or 30 years ago, and it seemed to me to be so far beyond me. But now, even though I'm in my late 50s, I've got more used to doing this stuff, and it was a pleasure to go up there and get on that wall. So I really love it. But I mean, cross country skiing, bird watching, anything that gets me outdoors, basically.
Well, I share the cross country skiing. I love it, and the bird watching. But I got to tell you, anything that would keep me off that wall would be good. And did you spend the night sleeping out there?
Well, we did actually. My on New Year's night, my wife and I decided we would go do an ice climb called Moonlight late in the day because it's often busy, and then we would bring our tent and then just sleep in that area for New Year's night. So I did start the year in a tent, which was a nice way to
Wow.
start.
Wow. Well, to me, that's great fun. Now, David, there are plenty of pessimists when it comes to climate change. It's pretty easy to get carried away with all the gloom and doom. Give our listeners a case for optimism.
Well, I have two cases for optimism, one human and one technological. The human one is the way young people are standing up and demanding action on climate. In a way, looking people like you and me in the eye and saying that we've been a bit hypocritical over the years, going to endless climate meetings and talking about action and not really doing that much. I happened to be in Ireland at some climate meeting during Earth Day this spring and saw these thousands of young kids marching in the streets with their amazing signs. And I was actually really moved to tears. And I feel like that climate change is hard and you need some level of political mobilization. I find that very exciting. The other one is hopefully a new sense of the power of science and technology under social control to solve problems. And I think this experience with the vaccine, with all its problems, really is amazing. The fact that this mRNA vaccine platform had been developed, for a decade, but nobody had actually brought one to market for real. And now we are actually have put them in the arms of, I think at this point, 10 million people or more, and done it in less than a year is absolutely extraordinary, not just for beating this pandemic, but because that is a vaccine platform and it's very easy to change the mRNA if you know how to manufacture the lipid capsule. This means that we've made humanity much safer against future lethal viruses by developing this new pathway to make vaccines very quickly. And that really is an extraordinary triumph of human collective action, of people in China sequencing the virus and then people, in Cambridge, Mass, using that sequence within days in Moderna to begin to develop the first vaccine. And I think it's a template for how people can work together, admittedly, with all the corruption and difficulty and, mess involved in this pandemic. It still shows you that you can work together and use these technologies in the human interest.
So, David, thanks. This has been terrific. You have a gift for demystifying complex issues, and I thank you for all you have done and are continuing to do to help us understand and to prepare for and combat climate change. So, thanks a lot.
Well, thanks very much. And thanks for you doing these podcasts. I think it's really interesting to get people with a policy background like yours, getting people to think about these questions. So thank you.
You have listened to Straight Talk with Hank Paulson, a podcast of the Paulson Institute. To find more episodes from leading thinkers and doers, please visit paulsoninstitute.org/straight talk or download on Apple, Google Play, Spotify, and Stitcher. And don't forget to rate and subscribe. Thank you for listening and see you next time.